Okay, so I think we started a little late, so I will try to cut my talk a few minutes shorter, but I might still need to go a few minutes into coffee break. So basically, I will talk about the exact same topic, except I will make my life a whole lot easier by not trying to prove lower bounds on communication, which is incredibly hard. Instead, I will just basically provide coding schemes, right? So I will show that we can actually achieve pretty good capacity. And to answer your question, I think we have the right answers from the upper bound side. So I think we know exactly what the capacity is, both for the adversarial case and the random case. Proving that this is actually the right thing. Most of the work is done, actually. Most of the machinery should just work, but so the little last step is not there yet. Okay, let me first maybe quickly connect it back to kind of the notation and the pictures that I had used yesterday, just to refresh the memory. So we want to do error correction for two-party interactive communication, right? So we have Alice, Bob, they talk back and forth, and compute something. And now we want to consider the case that there's some fraction of errors here. And for today, we want, for this talk, we want to think of the errors to be reasonably small. Okay, so last time we looked at kind of what is the maximum amount of errors that we can tolerate. Of course, if you go to the limits and the communication needs to blow up a lot. The big question is all of the protocols that we saw last time, even if the error is small, even if the amount of noise goes to 0, the blow up is still huge. Some constant factor. 1,000, 10,000, I don't know. So even if there's just a single error or, like a handful of errors that we want to tolerate, we still need to essentially repeat everything 100,000 times more often. And what we want to see today is that, in error correction code, we know exactly how things scale, right? So if the noise goes to 0, then the overhead goes to 0. And something like this would be really cool, right? So this is the part. So let's think about smallish error. Let's say, for example, 1% of the whole communication gets corrupted, and in this talk again, I will talk about the harder case, so adversarial errors, right? Any 1% of this conversation can get corrupted, and we still want to be able to do this. Instead of talking n symbols, we want to talk alpha n rounds, and we want this alpha to be small, right? So in the error correcting code case, if the communication only goes in one direction, then alpha is how large? Independence on epsilon for small epsilon. So if I want to send n symbols over a channel with a noise rate of epsilon, how many symbols do we actually need to send over?
N over 1 minus h of epsilon. Yeah.
Yes. So, or kind of the blow up factor will be something of 1 plus h of epsilon. And in the adversarial case, when we're talking about code distance, we don't know exactly what this constant is. It's somewhere between 1 and 2. And it's a big open question to know what that constant is. Also in this talk, we will not be able to determine second order constants. So this is what we have in the case. And now, as Ran already said, this does not, the same trade. So this goes to 1 as epsilon goes to 0. So that's great. We cannot achieve the exact same trade-off or similar trade-off in the interactive case. So let me just kind of go over what is the things that we know. So basically, so what we know is for random, what we can prove from the coding scheme side is that for random errors or oblivious or computationally bounded, anything that we can make oblivious, like a computationally bounded adversary, for example, if you have shared hidden randomness, the capacity will behave as 1 minus square root of epsilon. That we can prove that this is tight is a conjecture. Okay. In the adversarial case, it will be 1 minus square root of epsilon log 1 over epsilon. This we can prove. That this is, I conjecture this is tight. Like the square root of log 1 over epsilon factor is is needed. And there's a little bit of an annoying thing going on with the whole communication order thing. So let me just spend a minute to try to clarify what the problem is. Usually, so far we've only looked at alternating protocols. Why? Because it was essentially without loss of generality. We can take a general protocol where the communication order is whatever we want and just pad it to make it alternating. Right? So it loses us a factor of 2 in the rate. It makes a protocol at most a factor of 2 longer. So far we didn't care about rate. That's perfectly fine. It's without loss of generality. If you care about rate, then this reduction of kind of just like, if you want to talk twice, let me say nothing in between, that we can't do anymore, right? So now we need to distinguish, do we have an alternating protocol or do we have a general protocol? And basically, I think you should really just stick with an alternating protocol. So then you just need non-adaptive protocols. Life is simple and clean. Or if you want to simulate general protocols and you want to talk about rate, it's possible you can do it if you allow Oh, did I mess this up? If you allow, oh yeah, I did. Yes.
So, right, there's alternating, there's fixed order, but not necessarily alternating, and then there's anything goes.
So the input doesn't need to adapt. There's no noise to adapt to. So there's no notion of like, is the input adaptive or not adaptive? The input has a fixed communication order, and either it's alternating or it's whatever you want. There's no real, like, what would you adapt to? The original protocol is in the noiseless settings. There's nothing to adapt to. Right? So for the input protocol, we can either say it's alternating or it's an arbitrary communication order.
But it may be adaptive in the sense that, first player sends some bit, and then depending on what bit sent, the second player may have different orders.
Sure. That is still called a fixed communication order. It's very clear from the transcript, at any point of time, both parties know who should speak next. There's going to be no confusion, because where would the confusion come from?
No, but when you are then trying to adapt to errors.
Yeah, so when in the simulation, we can talk about adaptive or non-adaptive. And all I'm saying is that if you have a nice protocol to start with, so it's alternating, you can simulate it non-adaptively and get the perfect rate. If you have a general protocol, then either you do it non-adaptively, or actually you cannot hope to get close to a constant. Okay. Anyway, I keep this up. Let's keep this offline, right? Just think of the protocols being alternating, and don't be confused by the fact that we're proving, like lower bounds than the impossibility results, because they're kind of in different quadrants here. Okay, cool. So these weights are, so getting the right weights is cool. But the reason why I really like the things that I want to show you is not just because they achieve the right weights, but because they're dead simple. Right? So the protocols that we had here, if you want some computationally efficient, you need to start with a tree code, brute forces, then do ANOPS protocols, then boost it, then do the reduction, and it's not particularly simple. What I will show you is super simple. You can explain it to your mom. Right? No, really. And it's going to be like 5-line algorithm, okay? More or less. So here's the idea. If you want to, so what's the problem? If we run the protocol without any coding, then at some point errors happen, we might misunderstand each other, and might walk down the whole completely useless path in the protocol. Right? So here's the simple idea of doing coding for interactive communication. Run the protocol as if there's no noise. Have your conversation, do no coding, just have your conversation as if there's no noise. And every now and then, check whether we're still on the same page. If you're not on the same page, try to backtrack to a stage where we were at the same stage. If we seem to be on the same page, continue. Right? Makes plenty of sense, right? I mean, that's probably more or less how we have conversations. Not like we add like a lot of redundancy to it. No, we just have the conversation. If at some point we realize that there's something fishy, we find a step where we've still agreed. Okay? So now that seems like a very fluffy big idea. So let's actually write this down as a concrete algorithm. Okay? And it will give you completely formal algorithm, and we'll prove it. There's one simplification that I will make. I will assume that the alphabet over which we work, the alphabet size of the input, and the alphabet size of the simulation is logarithmic. Okay? So instead of communicating bit by bit, we're communicating over words. Okay, I send you log in bits, you send me log in bits. The idea is that it makes everything much cleaner. Okay? So here's a simple coding scheme. And yeah, so as I said, log of sigma is log n. So now that's the only simplification. Now let's write down more formally what I said. We repeat a bunch of times. We do this we pick some block length b. Okay. Think of b. B is going to be like something like 1 over square root of epsilon. It's smaller than the noise. So if the noise is 1%, yes?
The original protocol that you're trying to simulate,
Input.
That's called input. And each alphabet is this, or is it the simulating protocol that's going to use?
We use the same alphabet.
You're going to use
Actually, we kind of have to use the same alphabet because we cannot. So that's also why anything with 3 codes is kind of problematic, because we cannot hope to reduce the number of rounds. And if you use a larger alphabet, then that's already killers in the rate, right? So we really think of So the final result will work over binary alphabets if you want to. But here we're making our life easier and we work over large alphabet. It's the exact same alphabet, and it kind of has to be. Okay, so we have a block length, and that block length is larger than 1. It's chosen in such a way that we cannot have kind of 1 error in every block, right? So if the error rate is 1%, then we can have an error in every 100 blocks, in every 100 steps, and we choose b to be square root of that, so like 10 blocks wide. So we operate, so we have n over b plus a little bit of extra number of iterations. In each iterations, we continue our conversation, our original protocol p, b for b steps. And think of we keep track in our head what the conversation is so far, so we keep a transcript. Keep some transcript T. Okay? Now, after we have communicated for a bunch of steps, we want to check whether we're on the same page. What do we use to check whether we're on the same page? Hashing, right? So we do the usual thing. We sample independently random some seed. So let's say I describe this for Alice. Alice samples a log n size seed, and it sends over. She sends over the seed and the hash transcript, right? So she hashes the whole transcript according to the hash function that belongs to the seed. Let's call that h of a, and we send this over. And Bob does the same thing, so we receive the same kind of transmission from Bob, right? Receive Bob, we receive Bob's seed, and we receive Bob's hash. And I write primes here because these things might get corrupted, so we're not sure if we actually received the right thing or not. Okay. Now, what should we do? We should check whether we are on the same page. What does it mean to be on the same page? If so, what are we checking? If they agree, so what do I compute?
You hash your own transcript with the other's seed.
Yeah. So I take the hash function according to the seeds that I received from Bob. I apply it to my own transcript, and hopefully, if no errors happen whatsoever, then this should be the same as what Bob computed on his side. If this is the case, we're very happy. If this is not the case, something went wrong, and we should go back a bit, right? So what exactly do we mean with go back? Well, first of all, most likely the errors happened in these last B steps. So let's just remove those from the transcript.
Sorry, why is it okay if it is equal, but it could be that SA does not equal SP prime?
Oh, if they're equal, might be that there were many errors and we were unlucky in not catching them. It might be that there were errors in here and the transcript was also corrupted. I mean, we have an adversary, right? The adversary could have corrupted the hashes to make us think that everything is in order, even though it's not. All of these things can happen. But at least, yeah. I mean, we will prove that this works. So we remove B steps from the last B steps from T, from the transcript. And just removing the last steps for exactly the reasons that he said cannot work, because it might be that an error happened above. The adversary did not make us catch it in this round, and then we continue further. The error is going to stay there if we never go back, if we only remove the last B steps and then compute new one, remove them, compute new one, remove them, will never work, right? So at the very least, let's go another B steps back, another block back, right? Remove the last block and remove extra B steps. Okay, and this algorithm almost works. There's one place where it doesn't work, which is fairly easily drawn. So the problem is, once we get out of sync, we might never really get back into sync. Right? So what can definitely happen is that we have a conversation, we walk down the tree, then at some point I continue, because for me the hash looks fine, or we diverge, let's say. One party starts backtracking, the other party still starts going down. Right? So this can definitely happen. So we end up with something like this. Now, if no errors happen now anymore at all, we would realize that an error happens, we go both back 2 steps. Whereas errors happen, we go back here. Now, we're on the same path, but at different depth. Still, the transcripts don't match. If we now backtrack both 2 steps, we don't get any closer, right? We would backtrack 2 steps and chase each other all the way to the beginning. So that's kind of stupid. So let's avoid this. How do you avoid this? Who should backtrack here? The deepest one, right? So how do we modify this thing to avoid this problem?
Tell each other how deep we are.
Tell each other how deep we are. So instead of just sending the hash, we also send the length. Let's say, yes, the length of the transcript. And we receive a length, or something that's supposed to be a length. And here, instead of having both people go the extra back step, we only go back if he is a deeper one, if he is supposedly the deeper one. Right? So here, if the transcripts don't match, we definitely don't keep the last B steps. But if he is a deeper one, then we backtrack an extra step. So if my length is larger or equal to the reported length of Bob, then I go the extra back steps. Okay. Now this works. This is the whole protocol, and it works for adversarial errors. Yes.
Sorry, you're going to talk about what happens if the adversary is messing with things?
Yes, so let's prove that it actually, I mean, there are very reasonable concerns, right? Because now we're kind of trusting that we do the right thing. So this works. This is the whole thing, and we can prove it hopefully just on this board. Yes?
So what you gave here is randomized. If the noise is also randomized, can you fix the randomness here to get a deterministic scheme that works for random noise?
There is I don't know. Need to think about it. So I don't know. Let's
With random noise, can't we actually just use an error correcting code at each step if it's a polynomial size alpha?
Yeah. So not really in the sense that like corruptions here are still over the whole alphabet, right? I mean, like the adversary gets to replace a whole symbol by a completely different symbol, and that counts as one error. So error correcting codes would still not solve that problem.
The large alphabet is just for illustration, right? This actually works for binary.
This will work, yeah. I mean, it becomes much cleaner with a large alphabet. This conveys all the ideas without the, and I talk about it hopefully in, well, okay. Let's first prove that this works, okay?
Could you just go through the last two ifs?
Yes. So we take the seed from that we received from the other party. We use the same hash function if the seed was received correctly, and we hash our transcript, and we check whether we get the same outcome as the other side. If the seed is correct and everything, then this should, and there are no errors so far, then this should match. If it doesn't match, then something went wrong. So we definitely do not, we remove the last B steps that we communicated. In case there was an error higher up, we also want to go back. We don't want both parties to go back the same amount of steps because it's a chasing issue. So we ask each party to also report the length of their transcript and only have the deeper one go back. It's reportedly, like all of this is that's why they're primes. But.
So who's executing the last 4 lines? It's Bob?
Both independently on their side. It's the same protocol for both of them, and they just on. Yeah.
If you corrupt the value of t, then they could both think that they are.
Absolutely. Yeah. And against an adversarial error, it's totally possible that we diverge by n over epsilon many rounds. Right? Say n over epsilon errors that can be applied. The adversary can apply them all to the beginning of the protocol and completely fake us out. The first epsilon fraction of the protocol might be completely made up. The divergence can be as large as n over epsilon. It's completely unavoidable. But then it has used up all its error. We will realize it, we will backtrack, and then walk down. In this case, it works, and we want to say that this works in general.
So the adversary doesn't know the seeds that will be used in the future.
The adversary doesn't know the future. Yeah.
Sorry, so I'm trying to understand why you remove an extra B steps and you don't try to synchronize at that point. So you received some length of transcript.
For example, what we could do is, we already get a reported length, right? If the other party says there was an error, we know that there was an error, and it says, hey, I'm at this step, why don't I jump to this step? The reason why you don't want to do this is because this length might be completely made up. So the adversary could just, with a single corruption, could say, hey, look, there was an error, and hey, I'm at the very beginning of the protocol. If you take that for face value and you jump to the beginning of the protocol with just one error, I've killed all the progress you've made, so that's why you don't want to do this. So that already that already kind of goes into the right direction, right? So what we want to say is that now the steps that we make are only local. Yes, the adversary can make us go into the wrong direction in an arbitrary bad way. We will never step very far. Right? And because the block length is small, the adversary can only corrupt 1/10 of the block. So it can't make a step in the wrong direction too often. It can for a while, but overall it cannot make a step in the wrong direction too often. And that's why this works. So let's prove that this works. So the way we prove this is just by using some kind of potential. Right? We're saying that if the adversary invests errors, it can make us go in the wrong direction and decrease our potential, but if it doesn't, then we make progress. Okay? So if you just look at conversation, kind of our situation right now is we are consistent up to some point, and then at some point we diverge. We might be at different depths. We don't know. And we want to assign to this a potential. What would be a good potential to assign to this situation? How much progress have we made?
Number of links where you agree.
Yeah. So let's call the number of links that we agree L plus.
How much noise we wasted?
How much noise we wasted? We could put this into the potential. We also kind of have to look at how much we disagree, right? Because we have to work to make this go away. So
minus the 2.
Yeah. So let's call whatever the length of that we disagree. Let's call this L minus, and simple potential L plus minus L minus. Okay. So now let's prove that good things happen to this potential. Okay. So lemma 1. If you have no error and no hash collision, like we could also have, I mean, this will happen very unlikely. We can essentially treat hash collision as if they were errors because they don't happen too often. So if I will just call them errors. Right? So if you have no error or no hash collision, then the potential goes up by at least 1. That's a claim. And that's just saying that our algorithm doesn't do any, I mean, if you don't interfere with it, it does the right thing. So why is this the case? Well, it's basically only two things. Either we are at the same point. In this case, we will compute the next B step. All the hashes will match because there are no errors. And we will have added one block. Oh, yeah, let's count this in number of blocks. Right? We have added one block to our length. L plus increased by 1. L minus is still 0. Everything's good. On the other hand, if we're somehow on different pages, we will walk down, we will realize that we're on different pages, we will remove what we walked down, and then the deeper one of us, or both of us, will backtrack at least one step. So this will decrease L minus and keep L plus the same. So again, kind of potential increases by 1. So now we need to show that no matter what the adversary does, it can't make us go too bad, right? And basically, any iteration, no matter how much, how badly and how weird and how many errors the adversary invests in one iteration, it cannot make our potential go down by more than a constant. Right? So any iteration decreases by at most 3. So it's clear that there's some constant because we only, we only go steps in one direction. Not that it's 3 and not 4. It won't really make a big difference. You can just go through all the cases. The worst case where how you can actually get 3 is, let's say, if we're at the same spot when we perfectly agree, but now the adversary makes me go back and you go forward. Now L plus decreased by 1. And then minus went from 0 to 2. So this is how the potential decreased by 3.
Sorry, these steps, that counts as a count?
Yeah, so let's call it counts as in number of blocks. Yeah. Okay, and this is it. I mean, this basically proves correctness. I mean, now we just need to count, right? So and see that we run for enough rounds. So how do we prove correctness? Let's look at the final potential. The final potential, basically in each round, we make, by default, we make one progress. So how many iterations do we have? n over b plus 8 times n epsilon. In every round, and then there, whenever an error was introduced or a hash collision was introduced, we instead of going 1 forward, we go 3 backwards. Right? So we need to subtract 4 times. Now, how many errors can happen in total? This protocol will never run more than 2 times n rounds. Right? I mean, we want to achieve good rate. We'll actually achieve 1 plus square root of epsilon, but definitely not longer than 2 times n. We get an epsilon fraction of errors. And yeah, I don't know why I wrote this so small. I thought I had to divide by something. This is the number of rounds where we can get an error. Well, this 8 was conveniently chosen that this cancels out. So this is at least n over b, which means at the very end we agree on n over b blocks, which means we agree on what we want. Okay. So this proves correctness. And now the last thing that we want to check is that this is fast. Right, that this achieves a good rate, that the alpha, the blow-ups that we have is what we want it to be. So now what's the time? We have, so big N, the number of rounds that we run, is the number of blocks. So N over B plus some constant times N epsilon. And each iteration is how long? Well, it's B rounds long plus a constant number of rounds for this. B plus 2 in this case, but let's not care about the constant. B plus order 1. So we multiply this out. This is n times 1 plus some constant. And then there are 2 terms. One is an 1 over b term, and one is an epsilon b term. Okay. Now, we want this to be as small as possible. How do we choose b? We can choose. How do we choose b to make this work out?
Make the 2 guys equal.
One makes them equal, and then b becomes kind of 1 over square root of epsilon, right? So which is exactly, I mean, you know, I told you to begin with, but this is the reason why we choose it to be 1 over square root of epsilon, right? So this becomes 1 plus square root of epsilon. Okay. And this is, I mean, this trade-off is very intuitive. So you're losing rate in 2 ways. You're losing rate by adding these basically constant number of things every b blocks. Even if no error happens, you lose a 1 over b rate just by adding that redundancy. If you make the block lengths too small, you lose too much rate. You're checking too often. On the other hand, whenever there's an error, you need to backtrack at least a whole block. A whole block of b things gets lost. And this whole potential analysis shows that in an amortized sense, it's not more than a constant number of blocks that get lost. Right? So for every error, the epsilon fraction of them, we lose a b because of the backtracking. Now we want to balance between them. And this is basically the same underlying principle in the lower bound. That's it, one of the 2 you need to.
There should be some dependence on the probability of failure.
No, this is an adversarial case. You always succeed.
Choice of seeds. Like if all the seeds were 0, then presumably.
Oh yeah. So what we used here is that the probability that you have a failure is, I mean, you can basically treat hash collisions as errors, because the fraction of hash collisions with very, very high probability.
So somewhere, you know, it's if you're tolerating epsilon errors, somewhere there should also be a term that depends on the probability of failure. The protocol will not always succeed.
It will succeed with high probability, right? I mean,
so what probability?
Exponentially high, 2 to the n. Actually, I think n to the n.
No, but
n to the 1 minus n to the minus n.
But one a hash function. Well, first, you're using the alphabet, the polynomial size alphabet size.
Yeah. So.
For the hash function.
Yeah. Yeah. So hash
function. Yeah, with 1 over polynomial probability.
Yeah. But we need more than epsilon fraction of the times the thing to fail, to lose. So that's really unlikely.
So 2 comments. No judgment here, but I don't think my mom could understand this.
No, this part not. But that you just have the conversation and you backtrack if you misunderstand each other, that part maybe.
she'll understand something. Yeah. The other comment is it's not quite clear when this thing terminates. You never said when they accept at the end of this algorithm.
Oh, no, you fix the number of rounds that you run. Right? I mean, we run for this many rounds.
What if you make errors in the last rounds or something? Like, what is the final output here?
Yeah, so actually, what can happen here is that I say, run this protocol for this many rounds, but the protocol is really only n over b blocks long. So what do you do if you come to the end of the protocol and I say continue the conversation? Yeah. Just send zeros. Just takes the original protocol and attach like a long string of zeros to each leaf.
Yeah, that goes back to David's comment, because then you're kind of relying on just one hash at the end. What if the error is at the very end?
No. So what will happen is that if no errors happen in the very beginning, you will go to a leaf and you will run deep down on the path. Basically, all the zeros say, yes, this is the right answer. Yes, this is the right answer. And then if the last stop fails, you will remove one of these confirmations. But you will still be very deep in this leaf.
So do you wait for a certain number of confirmations? Is that kind
No, you just run for this many rounds, for a fixed number of rounds, and you look at what leaf you end up. It runs for you. You fix the number of rounds to begin with. You tell me the error rate is 1%. I tell you, and the protocols that you want to simulate is 100 rounds long. I tell you I need 1 plus 10% of 100 rounds to do it. I will run it for exactly this many rounds. And that's it. Because also, if I don't fix the length, it's not clear how much budget do I give the adversary.
I guess the point is at the end, you don't have to be on the same leaf, right?
No, you will. I mean, this proves that you will be at the correct leaf.
I think that you added it. If there are problems there, then you will backtrack, but they may be in different places on that.
The leaf of the original protocol will be a prefix of both transcripts. That's the guarantee.
Yeah, so these are just zeros. So you might end up here and I might end up here, but we both will say this is the right answer. Yeah. So, so I think this is pretty much it. So the only thing that doesn't work here, the only thing that we made our life easier is the log size alphabet. And I think this is also if you try to go to a constant alphabet size, there are at least 3 reasons why it really looks almost impossible to bring this into the constant size alphabet, which is this part here, we use one symbol, right? You use a constant number of symbols to do the checking. And here we have log n bits, very convenient, right? But if you're going over constant size alphabet, we can only use a constant number of symbols for this checking procedure. If it's more than a constant, then each block will have, even with random errors, will get corrupted and never get anywhere. Now, the seed lengths, so we need to hash, in the adversarial case, transcripts that are at least order n long, because the divergence can be order n epsilon long. If you want to hash strings of order n, you know that you need log n bits of randomness. Right? So at least in one shot, you need log n bits of randomness, so that seems kind of hard. How would you hash an order n long string with a constant number of bits of randomness? Right? Same thing, we need the hash output to be if you have a constant, just a constant here, then we have a constant probability that a hash fails, independent of epsilon. Then why don't we have too many hash collisions? And the other thing is the length. If we cannot determine who's deeper, how can we coordinate, how can we get back in sync? But the divergence can be order n long. How can we possibly coordinate who's deeper, who's not, without sending at least log n bits of information? Right, so that, I think those are the only reasons, this is so simple, and people have tried stuff like this before. These are the only reasons why this is not the first thing that was ever done, and this is the end of the story. This is why, me included, there are tons of other papers that are much more complicated. But all of these 3 problems can be dealt with. And
also, it's randomized. It makes sense to ask for a deterministic simulation.
Sure, but you can get this non-uniformly deterministic if you don't care about rate. This is also very similar to Brachowski-Kalai, for example. This is more or less Brachowski-Kalai, except that they can't do things uncoded. Because they need to be of large logarithmic size, so they need kind of they need to use tree codes here, and everything becomes more complicated, and you don't get rate, and so on, right? I mean, the general idea of backtracking when something went wrong, that is nothing that I came up with, right?
I agree, but I think it's interesting to find a deterministic simulation that achieves the same results.
Yes. Yeah. Okay. Yeah. So, yeah, I don't have time to tell you how to actually get around these problems, but either read the paper or talk to me or, yeah.